Okay, welcome to the second session on type systems. Glad to be back. And so for our first talk, Chen will be telling us about greedy implicit bounded quantification.
Oh, thank you. Good afternoon, everyone. My name is Chen. I'm currently a PhD student from the University of Hong Kong. Today, I'm delighted to share our work, greedy implicit bounded quantification. This is a joint work with Shengyi Jiang and my supervisor, Bruno Oliveira. Mainstream OOP languages such as Java, Scala, C#, or TypeScript have polymorphic type systems with subtyping and bounded quantification. Take this Java code as an example. It defines a generic method main. It takes two arguments of the type S and returns a value of the same type S. The S extends comparable here defines a type variable S and gives a bound comparable to it. We may write the type of main in a formal way like this. Bounded quantification is used to give subtyping bounds to type variables, so the quantifier is only bounded to range over the subtypes of comparable. This is a widely used feature in OOP languages. However, there is little work on type-inference algorithms supporting it. Type-inference enables removing redundant type annotations from programs and can reduce the burden of programmers. When we write the code, the compiler fills the missing types for us and keeps our code very clean and concise and more readable. Take this code also in Java as an example. It processes a list of strings representing numbers and converts the strings into numbers and filters the even numbers. In this code, we don't need to provide the type annotations when using the function, map, filter, etc. One thing to note here is that the list functions are polymorphic. Here is the type of map function in Java. It introduces a type parameter R, takes a function from T to R, and returns a stream of type R. By type inference, Java will automatically instantiate R with integer since the return type of value of function is integer. And it can also infer that S has type string since numbers is a list of strings. The algorithm will propagate the known type information and conclude that S has type string. Type inference is very important in a modern programming language, but surprisingly, there is little work devoted to practical OOP type inference. Currently, most production compilers like Java, C# use algorithms loosely based on local type inference, and their algorithms are not formally studied, and some problems regarding unsoundness and incompleteness have been found. Scala 2 is based on an improved form of local type inference, namely colored local type inference. Though local type inference is the most widely used techniques for programming languages with bounded quantification, it suffers from some limitations. Next, we will identify these limitations in Scala 2 and compare it with our calculus F sub b. It's worth noting that the implementation of Scala 2 contains some improvements compared to the algorithms formalized with local type inference. It enables more programs to type check. Scala 3 has more improvements, but it has not been formally studied. Scala 2 type inference remains more faithful to the original work of local type inference, so we compare our calculus with Scala 2. The first limitation is no support for interdependent bounds. Local type inference forbids the inference of type arguments with interdependent bounds because they couldn't find a complete algorithm that deals with such kinds of bounds. Scala 2 provides some basic support for interdependent bounds, but it fails frequently. If we define two identity functions, ID phone is from type B to type A to A, but the bound of B depends on A. Another one is from int to int. In Scala 2, we cannot apply ID form to ID int 1. Because Scala 2 wrongly instantiates A with bottom instead of integer. B is instantiated to int. It doesn't conform to the bound restriction that B is the subtype of A to A, so it's rejected. In our calculus, interdependent bounds are supported. It type checks the equivalent program below. The second limitation is hard to synthesize arguments. We may define a map function in Scala like this. It has two type arguments and it takes a function from type A to type B and a list of A and returns a list of B. However, when it's applied to an anonymous function, it fails to type check. That is because local type inference requires the types of function arguments to be synthesized first, but we can never synthesize the type of this anonymous function. A workaround is providing type annotations to the function argument, like we can annotate x with int here. Our calculus can type check the program without additional annotations. When the type variable to instantiate appears invariantly in the output type, but the constraints are not enough to decide a unique instantiation, local type inference fails to provide any instantiations. In such cases, Scala 2 still infers a type, but the type can be meaningless. For example, when applying the function second to 1, the constraints are not enough to decide a unique instantiation of A. Scala 2 still infers the type of ID as bottom to bottom, but it's meaningless. ID cannot be applied further. While in our calculus, unification is deferred and the second one can be applied further. Higher rank type inference is an important feature. It's very useful when we would like to take a polymorphic function as the argument of another function. However, the subtyping relation employed in local type inference is restrictive and prohibits type checking in many programs with high rank types. In this program, K has type int to int, and G is a function that accepts argument with this type. We would expect that the type inference algorithm can implicitly instantiate A with int so that we can apply G to K. However, this fails to type check in Scala 3 due to its lack of implicit polymorphism. Our calculus has better support for high-rank polymorphism. It can implicitly instantiate the type variable A here with int, and the program succeeds to type check. Next, we will start to introduce our calculus. Our calculus extends the earlier work, elementary type inference with bounded quantification. It's a variant of kernel F-sub. Different from local type inference, it employs global type inference, so it's capable of solving long-distance constraints. It follows the similar philosophy as elementary type inference. We only infer easy instantiations and use explicit annotations for hard instantiations. So our system has the implicit instantiation for monotypes. Like the example we showed before, we can implicitly instantiate A with int. For hard instantiations, like polytypes, we use explicit type application to allow users to provide the instantiations. This is the syntax of our calculus. Compared with elementary type inference, the change is that the universal types and the type abstractions now incorporate a bound B to support bounded quantification. These are the declarative subtyping rules of our system. It's based on the previous higher rank polymorphic systems. The difference between our system and the elementary type inference is that we have the variable transitivity rule, and all the for alls now incorporate a bound. These two differences cause problems in certain important properties and motivate us to rethink the question, what kind of type variables should be considered as monotypes? With bounded quantification, if we treat all type variables as monotypes, transitivity breaks due to the variable transitivity rule. Type variables with for alls in their bounds, like the type variable B here, can breach two for alls types with different bounds, which is not accepted in our subtyping. So in F sub B, only type variables with bound top or monotype bounds are regarded as monotypes. In existing predictive higher rank polymorphism approaches, finding implicit instantiations is greedy. All such approaches rely on the property that monotype subtyping implies the equality of monotypes. This ensures that if the first instantiation works, then it must also work for subsequent instantiations. However, without care, the property easily breaks in the presence of more expressive subtyping relations, like bounded quantification. So in our paper, we present two variants of F sub B. In the first variant, only type variables with bound top are regarded as monotypes. With this monotype definition, the property holds, and we get a sound, complete, and decidable algorithm. In the second variant, type variables with monotype bounds are also regarded as monotypes. It breaks the property. For example, in this context, type variable A is a subtype of int, but A is not int. So this variant is sound, but incomplete. The benefit is that it type checks more programs. Finally, let me conclude the contributions of our work. Firstly, we proposed a declarative bidirectional type system with predictive implicit bounded quantification and impredicative explicit type applications. We have good properties like checking subsumption, and we have type safety and completeness with respect to kernel F sub. And for variant 1, we have a sound, complete, and decidable algorithm. Our algorithm employs a work list formulation inspired by previous work. For the second variant, with monotype subtyping, we have a sound algorithm. All the theorems have been mechanically formalized in the Abela theorem prover with about 25,000 lines of code. And we also have a simple Haskell implementation. if you are interested, you can find our implementation proofs and the extended version of the paper by scanning the QR code. Thank you.
Okay, thank you. If you have questions, please come to the aisles. We have microphones up front here. I'll start us off. So you were comparing a lot of your examples to Scala 2 and Scala 3.
Yeah.
Do you have plans for an implementation for Scala based on your calculus here?
Sorry, I didn't.
Are you going to add this to Scala now?
No. They use different algorithms, so it's hard to adapt our algorithm to Scala. We aim at a higher rank polymorphism system, so that's our target.
Okay. So,
hi. Have you considered extending your approach to support, say, dependent types? Is that feasible?
We haven't considered it yet, but if you have some good thoughts about that, we can have a catch up later.
Not really.
okay.
Hey, Magnus here. Do you know anything about performance of this system? Do you have reason to believe it would perform well or perhaps not?
I think our algorithms perform well because we don't have backtracking, and we already have a confluence proved.
With respect to target type inference, as it happened with the Java lambdas, does your system compare in some specific way?
I didn't get clear.
In Java, when you have a lambda, the type of the lambda is inferred from the context. It's called target type. So does your system handle something like that, or do you think there is any problem to extend it in that way?
We do support to have some type constraints in the context in the algorithm version of our system. Yeah, so our system would support that, I think.
Okay. Okay, let's thank Chen again.